draftsman would draw the deformed shape. So that is the technique they use. Okay, so here are the different orientations of my shell, and this will be the short one, this will be the sheared, and this will be the long one. And returning to very simple variations of my face, I have now drawn these little crosses for you. And what you see is that for this particular deformation ellipse, this cross is straight, this is straight, and these ones are all sheared to that way, but by different angles. You can see that this angle here is different from that one and different from that one. So if I would now go and measure the orientation of these lines, the symmetry axes, together with this shearing angle, then I'm going to get a curve. The orientation changes and the shearing angle goes up and then it goes down, back to 90 degrees. And this is what Bredin made. He produced a line for each of these angles, and he plotted here the different shear angle, okay, these shear angles, for all the different orientations. So every line here represents one ellipse, more and more flattened, okay? If you have a very, very strongly flattened ellipse, then the angle of shearing changes very quickly, then it goes back to 90 degrees. If the ellipse is not so strongly flattened, then you have a much, much smaller change. So what you do, and I think that in one of the tutorials you are actually going to do a Bredin analysis. You get a series of fossils on a plane, and then you go and measure the orientation of the symmetry axis of the fossil and how much they are strained, and you plot them in a diagram of orientation versus shearing angle. Okay? If you're lucky, one of the angles is 90 degrees, then you know that you have to start here. But otherwise, you just take this diagram and you move it around until it fits. Okay? So, I think you believe me that if I say that you need at least 3 measurements to find on which of these lines you are. With 2 you can do it, but it will be very shaky. With 3, and of course if you have 5 or 6, then you can very easily determine that, for example, your ellipse is this one, and then you can back out how long it is, how much it has been shortened. Okay, so this is the Bredin technique, quite famous, made in Aachen a long time ago. You can actually see that these are the original yellow publication pages that I scanned in for you. There are a lot of different strain analysis methods, all depending on what you have for objects. For example, if you have a sandstone, then you use the method devised by Norm Fry, quite a famous structural geologist from England. And what you do there is you take these sand grains in a thin section, you put a transparent sheet on it, and you mark the center of each of these sand grains. Okay. And then what you do is you do this again, but you put the center of your sheet on another sand grain. And then you mark again all the positions around it. And then you do it again and again and again. You put the center of your sheet on each of these sand grains and you mark all the other ones. And what you get if you do that, you get a cloud in which in the middle, in an elliptic middle part, there are no points. And then there is a kind of a stellar ring of a higher density of points, and that is the strain ellipse. Okay, now think just for a moment or two and try to understand why that is the case. So again, what you do is you take a transparent sheet, you put a little cross in it, and you put the cross on this one, mark all the other ones, move it to the next one, mark all the other ones, and of course it's now computerized, so you get it very quickly. The reason why you get this is because in a sandstone there are no small distances between the sand grains. Okay? If you have a sandstone and you take the center of each of the sand grains, you will not find a lot of distances which are very short, because the sand grains have a certain distance to each other. Okay? So in a sandstone which is completely undeformed, and you do this game, you will find a point-free area which marks the distance between grains. Okay, if we have all these grains and if we deform the sandstone, then in one direction we shorten everything. So we shortened this area. So this is nothing else than the orientation dependence of this distance between the center of grains, of each grain. And it is a very simple, elegant method. The Fry method is being used a lot because, of course, sandstone is much more easy to find than a deformed fossil. And more or less like this, there are many other methods. There is a whole book full of strain analysis, and in fact, the book of Ramsey and Huber has a very extensive collection. The main point that you have to take home after this lecture is that when you look at deformed rocks, you have to keep your eyes open for objects that allow you to measure the strain. Fossils, sand grains, whatever, long veins or fractures, they all have information about the strain. And if you have found these objects, then you can go into the book and find the method that you will need to do that. If we do this strain analysis in a real rock, we would like to analyze the strain in 3 dimensions. In 2 dimensions, a circle will become an ellipse. In 3 dimensions, a sphere will become an ellipsoid. Okay, so now what we will have to do, for example, using the Fry method, is to do this measurement in 3 different sections of the rock. We take a cube of the rock, cut it in 3 different directions, measure the Fry, and then we have 3 different ellipses in different directions, and we can put that together and reconstruct a straight ellipsoid. And if we have that straight ellipsoid, then we can represent it in a 2-dimensional space, and this is the famous Flynn diagram that I'm showing you here. It is a 2-dimensional representation of 3-dimensional strain. And what they have done is they have taken the ratio between the longest axis of the ellipsoid and the middle axis, and here it is the ratio between the middle axis and the shortest axis of the ellipsoid. And in this diagram, if you plot the strains, what you get is the cigars on this side, the ellipsoids which look like a cigar. Here you get the ellipsoid which look like a pancake, and here in the middle you get the ellipsoid which look like a surfboard. So they are not deformed in this direction, but deformed a lot in the other 2 directions. Okay, so I'm at the end of this lecture. Deformation can be described by this matrix, homogeneous deformation that is. If we want to represent heterogeneous deformation, then we have to find these representative elementary volumes, and for each volume we have to write down this matrix. So, for example, in one of these numerical methods to calculate deformation, there are many little cells. I've shown it to you in the last lecture, and for each cell there is a matrix. The output file of those simulations is a huge file full of matrices for every little cell. We have deformation in 3D I have shown you how you can undeform to use the inverse matrix. I have shown you how to superpose strains one after the other using the multiplication, and I've shown you a little demo of a spreadsheet with which you can go home and exercise to figure out how this all works. And then I have given you a little overview of how to measure strain in deformed rocks using the Bredin method, using the Fry method, and then how to represent it in 3D using the Flynn diagrams. Okay, thank you very much, and see you next week.